let me talk to you about planet formation. Okay, so we're starting our story in the good old days of 1994. In 1994, we knew of one planetary system. That was the solar system. Here I'm showing you some scaled, kind of stylized diagram of the solar system. We have 4 inner planets that are small and rocky. We have 4 outer planets that are giant. Unfortunately, Neptune and Uranus did not make the cut here. They're way far away. But you get the picture. So the orbits are shown as these line circles, and they're actually all to scale. So you can see that we have these 4 inner small orbits, and then we have much larger orbits. The filled in circles are the sizes of the planets, also to scale with each other, but not to scale with the orbits. And you can see the nice orderly planetary system that we have here in the solar system. We have the small planets that are on the small orbits and the giant planets that are on the giant orbits. Then 1995 happened. This was the year that the first exoplanet around a sun-like star was discovered. This was a pretty major discovery. This is the first time that we had seen what other planets are out there. It's pretty crazy that 1995 to now is 30 years. The field of exoplanets is younger than me. It's been growing really fast ever since. So to kind of show you the wrench that this planetary system threw in the works, here I am showing you the orbit. It's this teeny tiny circle over here of the new exoplanet that we discovered. And then the size of the planet. So this is completely different than what we have in the solar system. Again, these sizes of the planets are to scale, the orbits are to scale. From the solar system, we expected to have the small planets at the beginning or at the inner orbits, and the large planets, the outer orbits. This planet, 51 Peg B, has an orbital period of 4.5 days. So that means its year is just 4.5 days. Compared to Mercury, the orbital period is 88 days. And it's about the same size as Jupiter. Okay, so to help you to understand why we did not expect this and why this is so weird, I'm going to go through a quick few slides about what we think happens during planet formation. Okay. So when a planet forms, it forms at the same time as a star forms. So a star starts to form when a bunch of gas and dust in large molecular clouds start to collapse. When they start to collapse, they start spinning. And the common analogy that people use oftentimes is to picture an ice skater. And when this ice skater is spinning and has her arms out, she spins slowly. And as she pulls her arms in, she spins faster and faster and faster. That's just conservation of angular momentum. So the same thing happens here with our stars. As they start collapsing, they start spinning faster and faster and faster. So most everything pours onto the star and creates this dense star that has more than 99% of the mass in the whole stellar system. But some of that material, and in particular the material that's perpendicular to the axis of spin of that star, doesn't fall onto the star. So it resists that gravitational collapse onto the star. Then within this disk, a bunch of gas and dust and stuff is spinning and starts to stick to each other. These are called pebbles, and then these pebbles over millions and millions of years bang into more pebbles, become planetesimals, bang into more planetesimals, and become planets. If these planets get to some critical mass, they have enough gravity to start pulling in all the gas and dust around them. This is called runaway accretion. And so for the big planets, this is what happens. They'd have a ton of mass fall onto them from gas and dust. This whole model of planet formation is called core accretion, and I'm going to be talking about that throughout the talk. And then at some point, the star turns on, and what that means is just the star starts fusing hydrogen and helium within its core, has a lot of energy, and pushes away all of that leftover material, and you're left with a beautiful solar system. So zooming in a little bit onto that pebble accretion or core accretion model, here we have a nice slice of what that disk is going to look like. Closer to the star, it's a lot hotter. And so basically the only thing that can form solids is rocks. As you get farther away from the star, it gets cooler and you start to form some ices. So farther away from the star, you have more material in solids, so you have more stuff that can stick to each other and form these planetesimals. Ices are also a little bit stickier than rocks, and so they also stick to each other a bit more efficiently. And so that's kind of why we thought that our giant planets are farther away, they're beyond some of these ice lines, and they can more efficiently build up enough material to then start accreting that gas. Okay, so that all sounds really good. Do we have any evidence that this is actually what's happening? So these are some beautiful real images of protoplanetary disks. Just recently, within the last 5 or so years, a large radio telescope called ALMA started taking data, and we were able for the first time to actually resolve these protoplanetary disks. And we saw all kinds of really cool things. You can see here, there's a bunch of ring structures. There's disks at all different angles, so you can tell that they're kind of flat because when you see a disk edge on, it looks really skinny. This is a really cool ALMA image. It starts with a artist's impression of what a planet looks like, and the end image is actually a real image of a planet that was detected within a protoplanetary disk. So here we have our nice planet, and the planet itself has a little disk around it. It's like a mini scaled down system. And this is the real ALMA image. So you can see that there's a planet forming within this ring of the protoplanetary disk. Okay, so besides the images of these disks, do we have any other evidence that potentially core accretion is actually happening? So since that first discovery in 1995, we have discovered close to 6,000 other exoplanets. I actually work at the NASA Exoplanet Archive at IPAC, and we host data publicly available to anybody of every single exoplanetary system that we have discovered. So this is plotting every single exoplanetary system. So we want to know if core accretion is happening, we would expect most of the giant planets to be forming farther away from the host star. Here I'm showing on the x-axis the orbital period in days, and on the y-axis is the planetary mass. You can see there's some really tiny pink circles. So Jupiter's way up here, so it's at a larger orbital period and a larger mass. What you might notice is there's a really dense chunk of planets that are at short orbital periods but large masses. These are a bunch of different planets that we've discovered that have this same sort of architecture as that original exoplanetary system, and we have called these all the hot Jupiters. What this plot does not actually show you, so this is showing you all the planets we've detected. What this does not show you is the underlying population of the actual exoplanets. The planets, these hot Jupiters, are way easier to detect than any other planets. That's because they're close in and they're really big. So they have a really large effect on their host star. There was recently a study that tried to actually find what the underlying population of Jupiter-like planets were by correcting for all of these biases that we have in our detection methods. This study was led by a bunch of people at Caltech. And what they found, so here we have some bins of different orbital periods and the number of planets that they found per star. And what they found is between 1 and 10 AU, I forgot to say this, an AU is an astronomical unit, and it's the distance from Earth to the sun. So between Earth's orbit and about 10 AU, which is where Saturn is in the solar system, so between Earth and Saturn, that's where most of the Jupiter-sized planets are. About 2% of stars have these hot Jupiters, we think, and about 20% of stars have a cold Jupiter similar to the Jupiter that we have in our solar system. Okay, so based on all of this, there's a bunch of open questions still. I told you about the theory of core accretion. We have some evidence that points towards core accretion being real, but is this actually how planets form? If it is how planets form, how can we explain these hot Jupiters? There's about 2% of stars have these, so they have to form in some way. And so do they form in a completely different way than the Jupiter in our solar system, or do they form similar to the Jupiter in our solar system and then migrate? Either way, that would have really large consequences, especially migration. If you have Jupiter-sized planets that are migrating all over the place, moving in, moving out, that's really going to disrupt your solar system. Any planets, small rocky planets that are in the habitable zone could get scattered, they could get moved. So we don't really want a lot of Jupiters moving around. Okay, so how are we going to test these theories? I'm going to tell you about 2 different ways that we can test these theories, hopefully, and both of them just so happen to use exoplanet atmospheres, which is what I do for research. So we can test these theories. In the solar system, we have this really nice relationship between mass and metallicity. Astronomers have this terrible habit of making jargon that doesn't really make any sense to anybody else. And so astronomers call anything that's not hydrogen and helium a metal. Everything else we get lumped together. Hydrogen and helium is like 99% of what there is out there, so everything else is a metal. And so there's this nice relationship between the total metal content and the total mass. So Jupiter has the largest mass, and it has the lowest abundance of metals. It has a lot of hydrogen and helium. This makes sense with core accretion because with those small rocky planets, they never actually build up enough mass to start accreting hydrogen and helium. They're basically 100% metals. The larger the planet is, the more of this hydrogen and helium it's going to attract, and then the total actual fraction of metals goes down. So then besides plotting the total amount of metals versus the mass of the planet, we can also try to look at abundance ratios between different elements that are in these planetary atmospheres. So going back to our nice image of how we think core accretion happens in the disk of the star, you can kind of imagine how at different snow lines you would get different ratios of different elements because some things are in the gas phase and some things in the solid phase. So we think that as we move towards the water snow line, so the water snow line happens first, and then the snow lines for the major carbon carrier species, so carbon monoxide and carbon dioxide, those happen later. Those happen at cooler temperatures farther out. And so we think that around the water snow line, you would get planets that would have a lot higher abundances of oxygen. And then it's not until later, near the carbon snow lines, that you would get planets that would have higher abundances of carbon. Oh, and also by measuring abundances of the major rock-forming species, so this is like silicates, magnesium, iron, we can understand how efficiently these planets are accreting other planetesimals, since those are kind of in the solid phase throughout the disk. Okay, so how do we actually measure abundances in in planets? Most of the planets that we detect, we've detected through the transit technique. So we basically stare at a star and hope that a planet transits in front of the star, so passes between us and the star. When the planet passes between us and the star, it blocks some of the star's light, and you see a dip in the brightness. You can do this to detect a planet, but with transmission spectroscopy, we also use the fact that some of the star's light actually filters through the planet's atmosphere and creates an observable signature. So this is showing, oops, I think I have to actually click this. Okay, so this is showing what we might see if we observe the planet at different wavelengths. At different wavelengths, we might see a larger transit depth and a smaller transit depth depending on the wavelength, because different atoms, molecules, and elements, they have very unique spectral fingerprints. So they emit and absorb at very specific wavelengths. And so any wavelength where something that's in the atmosphere of the planet absorbs, the planet is going to look larger because it absorbs all that light and makes the planet opaque out to larger distances. So we can actually do that, which is really, really cool. This is real data of a hot Jupiter, WASP-39b. This was the first paper published with James Webb Space Telescope data of a exoplanet. And this is showing real data of the transit of a planet in front of its host star at a lot of different wavelengths. The data looks so beautiful. I actually kind of hate to show you JWST data because it doesn't even look real. If you had looked at previous data, you'd be like, yeah, there's a transit there. This one just looks so perfect. Okay. So if you plot up that exact data that I was showing you earlier of the transit depth versus wavelength, what you get is a transmission spectrum. So this is showing the transmission spectrum that was published in that first look JWST paper of WASP-39. So on the x-axis are the different wavelength bins, and on the y-axis is the transit depth. So anywhere where you have an increase where the transit depth is larger, that is where something is emitting or absorbing in the planet's atmosphere. And you can see there's this huge bump around 4.5 microns. When you look at down here in the bottom, the opacity, how opaque all of these different common molecules are at different wavelengths, you can see that carbon dioxide, the black line, has a suspiciously similar bump at exactly the same wavelength. And so this was taken to be the first clear detection of carbon dioxide in an exoplanet. This data also showed a high confidence detection of water in a planet as well. Okay, so now we know that there's carbon dioxide in this planet. How do we then say how much water is there? How much carbon dioxide is there? And then how much carbon in general is in this planet? So what we can do is we can compare these two models where we can tweak the amount of carbon that we put into the planet. So this is that exact same WASP-39 data, now plotted with 3 different models. In blue is a model where the abundance of all of the different elements is scaled to 5 times the abundance of the sun. So everything in the sun, we know the abundance pretty well. You multiply everything by 5 and make it in a planetary atmosphere. That's the blue line. In orange, you multiply it by 10, and in green, you multiply it by 20. So you can see that the data here fits best with a 10 times solar abundance atmosphere. You can see, especially in this SO2, sulfur dioxide feature, it's very sensitive to the bulk abundance. And so that feature clearly isn't fit super well by a 5 times or a 20 times solar abundance model. Okay, so now taking this exact same WASP-39 data and sticking it on our mass metallicity plot, we get this single data point here. So WASP-39 is another of these typical hot Jupiters. It is a little bit smaller than Saturn, and we're getting something like 10 times the metallicity of the sun. So you can see it fits pretty well with this point, but that's just a single data point. I have to say we are at the very early stages of being able to populate this plot. So I'm plotting a bunch of data that was taken before this WASP-39 initial JWST data set. Everything in blue is from the Hubble Space Telescope, and you can see that the error bars are really large. So JWST is doing way better than what we could do with HST. So with HST alone, it was very difficult to actually see if the data was consistent with our line or not. Also, I'm plotting some data points in black for a study that I was part of. That is using the Very Large Telescope, which is a European telescope in Chile from the ground. And you can see that in general, we see a trend where the larger exoplanets have less metals and the smaller exoplanets have more metals. However, it seems like there may potentially be some offset there. This is, like I said, very, very early. So I think once we have a lot more data from JWST, it'll be a lot more clear what's going on here. So stay tuned. Okay, now, besides plotting just the bulk metallicity, remember we are going to compare our abundance ratios. So with another recent JWST data set, you can see this one's from 2024. This is another typical hot Jupiter, again, 4 or 5 day orbital period, Jupiter-sized planet. And this time, instead of just plotting the total metal abundance, we're plotting on the x-axis a bunch of different abundance ratios. So Z is the total metal abundance. So you can see it's enhanced in all of its metals. But the carbon to hydrogen ratio is not enhanced compared to the sun, whereas the oxygen to hydrogen ratio is slightly enriched. And the sulfur to hydrogen ratio is very enriched. Compared to Jupiter in our own solar system, Jupiter is about uniformly enriched in carbon, oxygen, and sulfur. And so potentially this is pointing towards this hot Jupiter having either a different formation pathway or a different formation location than Jupiter did in our own solar system. There's, again, very little data that does this at this point. Every day, more data sets are coming out. So this is just one other example. And in this example, we see something a little bit different. So here in black is another hot Jupiter, WASP 121. And within the error bars, it's actually showing more uniform enrichment in all of these species. So here we have the carbon to hydrogen, oxygen to hydrogen, iron to hydrogen, and nickel to hydrogen ratios. And they all seem to be somewhat uniformly enriched. At least we don't see this really large scatter here. And this is a lot more similar to Jupiter. So at this point, we have a sample size of 2 that I'm talking about, so I really don't want to take away any trends. But potentially there's 2 different formation pathways here where WASP 121 formed more similar to Jupiter and then migrated in, and HG 189 potentially had some sort of difference in how it formed. Okay, so to summarize some key takeaways, the method for planet formation across exoplanet systems is not precisely known at this point. We think that core accretion does a pretty good job of explaining a lot of our observations, but exoplanet systems are really diverse. We've seen that they are much more diverse than we initially thought from looking at just our solar system. A key example of this is the many hot Jupiters that we've seen that are nothing like what we have in the solar system. Hopefully by observing exoplanet atmospheres, we can make key measurements of abundances and abundance ratios. And we do this for the most part using transmission spectroscopy. There's definitely other methods. This has just been the one that's been used the most. So then we can compare these abundances and abundance ratios to each other, so within exoplanets, to the planets in our solar system, and to the predictions from our model to try to say something about how planets form in general. And some key patterns that we've seen so far. It seems like there is some sort of mass metallicity relationship in exoplanets with the data that we currently have, but potentially there's some offset compared to what we have in the solar system. So maybe this is evidence for core accretion. And so far, hot Jupiters have shown different abundance ratios between each other and potentially with Jupiter. And so maybe this is saying that there are multiple formation pathways for giant planets. They don't all have to form at a Jupiter distance and migrate. There could be some differences in how these planets form. And that's all I have. So I'll take questions. Do I take questions now?